In section 6, we're going to be looking at understanding the graphs of functions. We're going to use the vertical line test to test for functions. We're going to find zeros, which are solutions of functions. We're going to determine intervals on which functions are increasing or decreasing, and look at relative maxima or relative minimum values for the function, which are also called local maximums and local minimums. We're going to look at average rate of change on a function, and we're going to look at identifying whether a function is odd or even. So looking through and talking about the graphs of functions. So this is a function, right? And we're taking a look at this, and when the function is composed of a bunch of ordered pairs, which normally we would call x and y coordinates, but you could also think of them as x and the functions of x, right? X and f of x. So this is just function notation, and this would be standard notation. So for every ordered pair, the values that we find for x and f of x are movements from 0, 0. So we would move x horizontally and f of x vertically. Okay, and that's how we do the ordered pairs. This should all be rather familiar to you. Okay, when we start talking about the domain and the range of a function, what you're looking at when you talk about domain is, are there any restrictions for values of x? And rather than examining the equation, which you've done before, now we're looking at the graph. Is there anything on this graph that limits using any specific x value from negative infinity through to positive infinity? And in this case, the answer is no. There's no restriction. There's no gap in the graph. There's no barrier on the right or the left side. This one's going to travel on forever in each direction. So this would be all real numbers for the domain. Now the range, not the range, the range is the collection of all of the outputs. And that relates to the y values, right? Domain is related to x, range is related to y. So is there a vertical barrier? Well, yeah, there is. Look right here, right? My graph does not go above this point. There's nothing up here. So you see that the maximum value of y is 3. So then the range would be that y is less than or equal to 3. I've got this barrier where I just stop and I can't go any higher than that. Okay, which should be typical of a quadratic. It either has a maximum or a minimum. So there's always a range limitation on a quadratic function. Okay, the vertical line test. The vertical line test is a test to see, is our function a function? Is the graph a function? And if I draw a vertical line, you see if I put my vertical line here, I hit the graph in 2 points. Well, this is not a function, because for this input right here, I have 2 outputs. In fact, for almost every input, I have 2 outputs. That's what the vertical line test finds. So this one here, not a function. So the vertical line test says that if I draw a vertical line through my graph, if I hit the graph at more than 1 point at any point along the way, it's not a function. Well, if you look at this one, as I take my vertical line across, it never hits the graph in more than one place. So this one is a function. And if I take my vertical line onto this next item, see, the fact that I hit nothing here is fine. I just never hit it in more than one place. I can hit it not at all, that's fine. And so this one is also a function. Oops, excuse me. Is a function. Okay, so that's the vertical line test. It's a very simple test, and it lets us find out whether or not the graph we're looking at is the graph of a function. If I want to find the zeros of a function, I'm looking for values of the function for which the output, meaning the y value, is 0. If I look at them on a graph, Those would be the x-intercepts. But in this case, I'm finding the values for which it equals 0. So I set the equation to be equal to 0. We do this all the time with polynomials. And in this case, I would want to factor this, probably would be what I would want to do. I want to find the factors of 2 are 1 and 2. The factors of 24 are 1 and 24, 2 and 12, 3 and 8, 4 and 6. And I want to find products of these factors that have a difference of 13. Well, 2 times 8 is 16, and 1 times 3 is 3. So that's a difference. 16 and 3 have a difference of 13. That's perfect. So I'm going to want my 16 to be positive. And as I go through doing this, I'm going to take this away now that I've done that. I'm going to make 2 binomials. I'm going to put 2x there, and I'm going to put x there. And I know that one of these signs is plus and one is minus, and I know that because I need the 16, this is going to be plus 8. I need the 16 to be positive, and I need the 3 to be negative. Okay, so I'll have plus 16x and minus 3x. Those combine to become plus 13x. If I want to go ahead and continue on with finding the zeros in this case, I would set each of these to be equal to 0. If I have 2 items that are multiplied together and the result is 0, then one of them must equal 0. Or I can always take the opposite of this item divided by the coefficient. So the opposite of the constant divided by the coefficient, opposite of negative 3 is 3 divided by the coefficient is 3/2. And the opposite of 8 is negative 8 divided by 1 is negative 8. Those are my solutions. Those are my zeros. If I set this to be equal to 0, I want the square root of t minus 25 to be equal to 0. And obviously, what value of t will make that happen? 25. Right? T equals 25. And on this one's a little interesting because it's a rational function. The things that will make it equal 0 are when the numerator equals 0. So I set the numerator to be equal to 0. So x squared will be equal to 2. So x will be equal to plus and minus the square root of 2. Those are my solutions, which are also called zeros, which are also x-intercepts. So when you see 0, or you find the zeros, or you see solve, they're telling you to do the same thing. If they ask you to find the zeros of the function, find the solutions of the function, find the x-intercepts of the function, they're all the same thing. Okay, if we want to look at increasing and decreasing functions, we're looking at what's happening as I look from left to right on the graph. From this point to this point, my graph is decreasing. From this point to this point, my graph is constant. And from this point to this point, my graph is increasing. So we call these intervals. You can say, okay, for this interval, it's decreasing. For this interval, it's constant. And for this interval, it's increasing. And that's how we evaluate these. If we took a look at graphing this function, and I'm going to go ahead and I'm going to use a graphing tool to do that. I'm going to go ahead and use Desmos to do that. I pop over to my graphing calculator and I'm going to go ahead and put that equation in. The equation is x cubed plus 3x squared minus 1. So I'm going to do x to the third power. I'm sorry, here I wanted x to the third power plus 3x squared. And I forget the constant. It was minus 1. Minus 1. And here's my graph. So if I want to find my intercepts, they're here. But when you look at the interval from negative infinity to negative 2, I'm increasing. right? My graph as I go from left to right is rising. So let's go ahead and put that in here. Right, from negative infinity 2 for this interval to 2, negative 2, my graph is increasing. If I go back from negative 2 to 0, it's decreasing. From negative 2 to 0, decreasing. And from 0 to positive infinity, it's increasing again. And if you go back to take a look at that, if you go back to take a look at that graph, you can see that generically speaking, if I were to sort of approximate this with a line, you can see it's got a very steep slope. It's mostly increasing. It just, for a second here, it turns around and it's decreasing, and then it goes back again. Okay, so that's all we're really looking at, is what is the graph doing at these different times. Those turning points are called relative or local maximums and minimums. So you could also call these local maximum is another way to say relative maxima, and local minimum is what you would use for this. So it's really the point at which we change from being, in this case, decreasing to increasing. There's this moment where we stop and we get a low point. When we change from increasing to decreasing, we get a high point. And that's what we're looking at for these. Okay? And so we'll approximate these. Normally we'll use a graphing calculator or something to find them. So if I take a look at this, the graph of this, I've gone ahead and put it into Desmos, and it's this blue graph. And if we want to find the local maximum here, or my relative maximum, we can see it's 6.063, right? It's a quadratic function, so it only has one. 6.063 would be the relative maximum. Okay, when we talk about average rate of change, we're talking about examining a section or a segment or an interval of a function, and we're basically picking points on the function and drawing a line between them. And when you look at this calculation, we're talking about slope. We're talking about y2 minus y1 over x2 minus x1, rise over run. So when you look at doing that for a section, we're basically saying, what's the change from here to here on the average? So you notice this is increasing to here and decreasing to there. So it has a positive change here and then a negative change there. And what's the average? That's what we want to look at. If we take a look at a problem like this, we're going to find I need to do an input-output table. So I'm going to use -3 and -2 for my first interval. When I plug -3 in, -3 squared is 9, plus 2 times -3 is just 6, that would be 3. And when x is 2, -2 squared is 4, plus 2 times -2 is -4, that would be 0. And when I find my difference, I'm going to have 3 minus 0 over -3 minus -2. So I have 3 over -1. So my average rate of change is -3. In our next interval, I'm going to look from -2 to 0. So here's -2. I've already done that. I know that's the output. When we plug 0 in, 0 plus 2x is 0. So you notice we have no change. 0 minus 0 over 0 minus -2. 0 over 2, which is an average rate of change of 0. So the calculation that we do is the same calculation we do with slope. And all we're really doing is we're saying between these 2 points, we're connecting them essentially with a straight line and finding its slope in order to find the average rate of change. We're talking about using the same idea to calculate average speed. We want to know the average speed if I'm going from 0, right, moving away from a stoplight from 0 to 1 second. What's the rate of change? Well, let's plug these two values in. I'm going to use 0 and 1. When I plug 0 into this function, I get 0, right? 0 to the 3/2 power is 0. 0 times 20 is 0. When I plug 1 in, 1 to the 3/2 power, or 1 to any other power, is 1 times 20 is 20. So when we look at the rate of change, we'll have 20 minus 0 over 1 minus 0, so my average rate of change is 20. And when we look from 1 second to 4 seconds, we've already got the 1, let's put in 4. 4 to the 3/2 power, well, the 3/2 power would be the square root of 4, which is 2. 2 to the 3rd power is 8 times 20. 8 times 20 is 160. So when we put that in, 160 minus 20 over 4 minus 1, that's going to be 140 over 3. So 140 thirds, right, which is a little over 40. Right, if I actually do the division, 140 divided by 3, 4, 12, 20, 46.66. All right, so you can see that the speed, which we know actually from physically doing this, driving away from a stoplight, it increases over time. When we look at tests for odd and even functions, it's really about finding out, doing a test with the opposite of x. And what we get when we try putting in x and the opposite of x. So it just depends on what we end up getting, and when we replace x with negative x, what do we get? So let's take a look at doing that. So when I replace x with negative x, I get 5 plus 3x. It's not the same as this, and let's go back to our test. It doesn't become the same function, and it doesn't become the opposite of the function, so this particular one, this is neither. It's not odd nor even. When I take this function, I say plug negative x into the 4th minus negative x squared minus 1, and I simplify it. Negative x to the 4th is x to the 4th minus the opposite of x squared is x squared minus 1. This is the same function. So if we go back a page, when it equals the same thing, that's an even function. So this one is even. And when I do see the same thing here, I'll 2 times negative x cubed plus 3 times negative x. Negative x cubed, negative x taken to the 3rd power would be negative x cubed times 2 is negative 2x cubed. And plus 3 times negative x is negative 3x, that's minus 3x. And you'll see this is the opposite of that. If I took that and multiplied it by negative 1, I get the opposite of 2x cubed minus 3x. So this one is odd, and that's what that looks like. Okay, so what we've done is we've gone through the vertical line test. We've looked at finding the zeros of function. We've looked at different intervals to determine them being increasing or decreasing. We've looked at how to find average rate of change in a function for an interval. And we've stated the definitions of even and odd functions.